I will make the deadline on 8:06, Monday, 8:06 a.m., not p.m., a.m. Now, however, I strongly suggest you to start working on it right away and not waiting until last minute, because strangely, things break down last minute and things don't go as planned last minute. Okay, if you purposely procrastinate, trust me, time will procrastinate on you. Okay, and yes, I need you to own it if you don't turn it in on time this time. Okay, and even though the deadline is Monday 8:06 a.m., please be aware on the same Monday you will have a test that I post at 7:45, as I remember. So what I don't want to happen is like you wait until very last minute to turn in your quiz, and it turns out that you don't have enough time for your test. Okay, you need to turn it in on time, and if you cannot take it on time, you cannot submit it by the deadline, then I will need to give you another test, and I have to call it makeup test. And as you can see from my syllabus, I only give one makeup test. So if you, let's say this Monday, you can't take it on time for some reason, probability wise, that's approximately 3% to happen, then it won't happen anymore in future for that particular student. Okay, now the reason is for a student to miss a test with a reasonable excuse, that's 3%. For the same student to miss 2 tests from the same teacher in the same summer is 3% to the power of 2. That's 9 out of 1 million chances. Okay, so the only time you can have 2 excuses, you need 2 excuses for tests. For my test, it's more likely that you purposely set yourself up for failure, and I don't want that to happen. I don't need another student like that in my class. Okay, you need to learn to manage yourself and own your education. Okay, that's the little announcement for today. And don't forget that you need to learn to turn in your assignment, your quiz, and later on your tests using PDF. Okay, now you have already more than 1 week to practice for that, and I hope these tests you know what to do. Okay, those kind of technical stuff should not be an issue anymore. Okay, yes, I get emails from I think from 2 students that you guys don't have a computer. Okay, yes, if you don't have computer, you can just use your phone and then write it on a piece of paper. Okay, it would be nice if you can print it out, but if you don't, then it will take you slightly longer time, and that's what my extra 15 minutes for, to write it on the piece of paper. I think let me share that page with you. A second. If you want to see the instruction for test 1, yeah, you can access that already here. Okay, make sure you see what I will expect from you. Okay, I will post it at 7:45. I will post it here. Okay, and you need to stop working at 10 o'clock, and you need to finish uploading it to Canvas at 10:15. Okay, at 10:15. Now, I will not extend the time. I will not extend the time. You need to have, it's not that you start uploading it at 10:15. No, you have to finish uploading it at 10:15. You need to hit submit button by 10:15. Okay, Otherwise, the system will reject whatever submission you have. Okay, and at that time, when I get an email, Thomas, I have this issue, I have that issue, that's your issue. Okay, you manage it. Okay, I have one wife, that's one problem too many. No, no, I hope you take it as a joke, you know. But I mean, at the same time, everybody have their own issue. If you push your issue to me, I will not take it. That's enough. Okay, that's enough. Thomas, you are so not understand. You are so not considerable. How much consideration should I put for a class of 40 students? If I have to think for 40 students and all their excuses, then who will care for me? Okay, no, you do it. Okay, yeah, and the reason I post this a lot earlier so that you can manage, arrange yourself, arrange your situation such that it's we can go through this smoothly. Okay, yeah, at some point you have to you actually do your part, dude. Okay, now let me go back to my note. And I will leave it here so that you can be aware of that. Yeah, actually, most students in this class currently not following my lecture live. They actually watch it from video, like the video clip that I post. I'm not video clip, the recording that I post, and that's totally fine. But I'm so afraid that they're the one later on that says that they don't have time, they have something happen. No, the thing is this though, legally and formally, this class runs from 8 o'clock to 10:05. So I have the right to expect you to be quote unquote present canvassly during this time, including taking your test during this time. I can enforce that. The fact that I let students not going live together with me during lecture should be taken as courtesy, okay? Yeah, and I just expect you to be live with me 4 times for test and 1 time for final. That's all I ask for, okay? But if all these 5 incidents you still cannot make any of that, sorry dude, why you chose this class, okay? Yeah. Yes, let me start with the lesson. Yesterday, we end up with me presenting the inclusion-exclusion formula or general addition formula. Inclusion-exclusion formula. That is probability of A or B. At least one of these A or B is probability of A plus probability of B minus probability of B intersection. I hope we have we remember why this formula looks like that. That's because set A intersect with set B. Okay, intersect with set B. Give us the situation where the probability for the union A or B makes it a probability of A plus probability of B, but then you see that the green part, it becomes green because it's double shaded, and therefore it must be because it's double counted. Now then, to make it only single counted, I need to subtract that once. Okay, that's why the formula looks like this. Now, please also remember that we did the probability of the union or probability of the intersection, the union to be more precise, yesterday without this formula when it comes to Venn diagram or contingency table. It is not because this formula does not apply. No, it still applies. It's just like you are working too hard while the information is right in front of you, easy to add, easy to subtract, it's easy to see. Okay, we only use this formula if we don't have contingency table or if we don't have a Venn diagram. Okay, now let's do some example. Let's do an easy example first. Suppose it's given probability of A equals to 0.7, probability of B is 0.6, and probability of D intersection is 0.5. Then what is the probability of the union of A and B? Now the way we answer this question, we will start with writing down the formula first. Okay, always write down the formula first. Probability of A union B equals to probability of A plus probability of B minus probability of A intersection B, and then we plug that in. I think this question is quite easy. Okay, and yes, I use A and B here just for my notation though, just for my notation. But I can change that event A or event B into something else. For example, I can change that event A to be the following. Let's say I have another example. The probability of what you call that, a proposal to be approved by what is good? By the director. Maybe let's start with the manager. With the manager of a company is 0.7. The probability to be approved by let's say the union, whatever it is 0.6. To be approved by at least one of them. Which means either manager or union or both, okay, is, let's say, 0.9. And find the probability that the proposal is approved by both. So if I use the notation that this is the probability approved by manager, and this is the probability of being approved by the union. Oh, maybe union is not a good one, huh? And this guy here, at least one of them refers to probability of being approved by manager or by the union. Let's say they were doing the early stage of some contract agreement. Okay, then the question is, what is the probability that both sides agree to that, approve that? So you see, suddenly we get to what we have earlier, right? Okay, so solution, probability of manager or union, at least one of them or even both, is equals to probability of manager approved by manager plus probability approved by union minus probability approved by both. And then we plug in numbers. At least one of them, that's 0.9, equals to probability by manager 0.7 plus probability approved by union 0.6 minus probability approved by manager and union, which is the question. Then I compute 0.9 equals to 1.3 minus probability of manager and union. So probability of being approved by manager and union at the same time is 1.3 minus 0.9, which is 0.4. Okay. One other case in which we may be able to apply this is the case of cards. Consider a deck of cards. Let me get a picture for a deck of cards. I know some of you may not know what is this. Use this one. Give me a second. Give you the picture of a deck of cards. This is a deck of cards. Okay, now it has 4 suits. It has 4 suits. And 13 denomination, or they also call that wait a second, I need to go back to the picture. That website has some issue. They also call that denominations or ranks. Denominations. So Blank. Okay, now we have ace, usually representing 1, or in blackjack it represents 1 or 11. 2, 3, 4, 5, 6, 7, 8, 9, 10, and jack, queen, king for each suit. A total of 52 cards, not including jokers. Now suppose we have this deck of cards, a deck of 52 cards. And suppose I ask find the probability of selecting one card that is a heart or a queen. So you select one card at random. What is the probability you get a heart card? There are 13 of them, right? There are 13 of them. The heart card, there are 13 of them. Or a queen, there are 4 of them. You see what I mean? Okay, now notice that this will be the way we answered it before. It was like 13 plus 4 minus intersection 1, because the queen heart is double counted, right? Okay, it's counted in that 13, also already counted in that 4. That is 16 over 52, which is 4 over 13. Now, if we break this down, notice that this is actually the same to say 13 over 52. That's the probability of getting a heart, plus 4 over 52. That's the probability of getting a queen, minus 1 over 52, which is the probability of getting a queen heart queen. Okay, so this is probability of heart plus probability of queen minus probability of the intersection heart and queen. Okay, basically instead of having 17 cards that are heart or queen, there are actually only 16 of them. Okay, because there's one card that is a queen, also a heart. Now, that's one application of inclusion-exclusion formula, into playing cards. Now, what happens if the events are disjoint? Let's say probability of getting jack or king. They are disjoint. Why? Because there's no jack that is a queen. There's no jack that is a king. There's no king that is a jack. Okay. So the general formula is supposed to be probability of getting a jack plus probability of getting a king minus probability of getting a jack and a king. Now, however, this will be 0 because jack and king has nothing in common. If that card is a jack, it will not be a king. If that card is a king, it will not be a jack. Okay, now then from there we go on computing probability that we pick a card that is a jack is 4 out of 52. Probability of getting a card that is a king, that's 4 over 52. Computing further, that's 2 over 13. Okay. Now I will go further, making it a bit more complicated. what we will do right now, probability of selecting more than one element without possible repetition. Without getting the same item twice. Okay, now let's say we look back to that cards problem, going back to that cards problem. Consider a deck of 52 cards. Now in this class, when I say 52 card, a deck, it refers to 52 card deck, okay, not 54. We don't include the jokers. Okay, consider a deck of 52 cards. In an experiment, of selecting, make it easy first, 2 cards without replacement. Now, without replacement means the card that you selected, the card selected in first place is not put back into the deck. Therefore, that card cannot be selected in second place. Okay, so we don't, whatever card we pick earlier, we will not put it back. Therefore, it won't be selected the second time. Suppose we have that action. Suppose then part A, what is the probability that we get both diamond, for example? So we select 2 cards, right? What is the probability when we select 2 cards, both of them diamonds? How many diamonds card? It's a suit, right? It's a suit. There are 13 cards. There are 13 diamonds out of 52 cards. So the probability that the first one, we will pick it this way. We'll pick twice, right? The first will be out of 52 cards, right? Now, after you select that one card out, the second time you try to pick it, there will be only out of 51 cards, because one card's already out. Okay, because one card already out in the first place, right? So the probability that the first one is diamond is 13 out of 52. That's the probability first is diamond, okay, times how many diamonds left if you pick the first one out? There are 12 of them, right? 12 of them. And then how many cards left in the deck after you pick the first one out?
51, right?
Only 51, that's right. So Then the probability that you select two cards, you do it one by one, okay? You do it one by one without replacement, and both of them turns out to be a diamond is given by 13/52 times 12/51. Now, when you use your calculator, you will get this is equal to 0.05882. Okay, this is the probability that the second one. Now, using the same idea, try this. What is the probability? So we do the same experiment. Okay, we pick two cards. Without replacement. What is the probability that both of them, let's say, both of them aces? There are 4 aces. Okay, I hope you can fast enough memorize this table, this diagram here. What a deck of 52 cards look like. There are 4 aces. What is the probability that you actually get double aces, both aces? And after you're done with that, let me ask you to try. What is the probability that you get, let's say, jack first? Then queen. Okay, let me give you 2 minutes for this. Okay, what is the probability that both of them aces? How many aces in a deck? 4 out of 52. That's the probability the first one is ace, right? Times the probability that the second one is ace is 3/51. Okay, I think I can reduce this first. This is 1 out of 13 times 1 out of 17. So in fraction, there will be 1 out of 1 out of 221. That is 0.00452 for 5 decimal places, right? Okay, now what is the probability that you get jack first and then queen? Jack first, that would be 4 out of 52, right? And then after that, how many queens left? That's right, actually there are still 4 queens left, but out of only 51 cards. Okay, that will be, let me see, 16 divided by 52, the product of 52 and 51. That will be 0.06, I'm sorry, 0.00603. Now, notice that in part C, the order is important because this is the probability of getting jack first and then queen. Now, how about if I change the problem? Seems to be similar, but they are not. The probability of getting a jack and a queen. What's the probability of getting a jack and a queen? Now, the thing is, to get a jack and a queen, there are actually 2 ways. Either you get jack first, then queen, or plus you get queen first, then jack. Okay, so there are 2 ways to get a jack and a queen. Jack then Queen or Queen then Jack. Okay. Now then, when we compute the probability, you will see that the probability of the first event, we already counted earlier in part C, plus the probability of the second event. If you compute it, you will see you will compute it the same way and therefore come up with the same decimal. Actually, because of rounding, I will get 0.01207 because these were 3 here. Yeah. So when I add them, it becomes 66, right? 0.012066. And when I round it to 5 decimal places, it becomes 7. Okay. Now notice that you can easily change this question here into the blackjack case. Now, before we handle blackjack, probability of getting a blackjack. Now, blackjack is an event where one card is a 10 or jack or queen or king, and the other one card is an ace. Okay, and for us to get a blackjack, basically you get these cards. Then we'll consider the probability of getting that 10 jack queen king then ace plus probability of getting ace first then 10 jack queen king. Okay. Let me give you 1 minute at least to have a feeling about it. Probability is actually not only something you do theoretically, it's something you apply. Okay, those numbers, those probability becomes meaningless unless you apply them. Of course, when I say apply it, it also means because you know probability, we will see that especially in chapter 6, because you know probability, you will not gamble unless you become the dealer. Okay, the risk of losing money when you go to a casino is extremely high. Okay, yeah, but I will explain it later on. Let's see this one here. Probability of getting 10 jack queen king and then ace. 10 jack queen king. How many cards for 10 jack queen king? Four times 4. That's right. There are 16 cards over 52 times 4 aces out of 51. Okay, and then for the second event ace then, that face value, that will be ace first, 4 out of 52 times 16 over 51. Okay, we compute that 16 times 4 over the product of 52 times 51. Make sure you know how to use your calculator. So I get 0.02413 plus 0.02413. Basically, I multiply that by 2. It gives me 0.0482765 actually. Okay, that's the probability of getting a blackjack. Now let's apply this idea here to the Venn diagram we learned yesterday. Let's say, for example, I have a Venn diagram. I don't remember what we have yesterday, to be honest with you. So, but let's see. Let's say we have Venn the Venn diagram consisting of people taking math and people taking English. Let's say there are 5 people taking both, and then 7 people taking math only, 8 people taking English only, and then 10 people taking neither one of them. So a total of, I think it should be a total of 30. A total of 30 people. So when you play blackjack, you can do most of these probability problems in your head based on just cards on the table. Yes and no. I did this. I say yes because yes, I base that on what we have on the card, on the table. But do I compute the exact probability the way I did it here? No, I do estimate. Okay, there's something called conditional probability, and of course, the number of cards you have on the table is more than just 2, right? When you play, actually you get, even if you yourself on the table, there will be actually 2 players, you and the dealer. Okay, so when we play blackjack, for example, we can see 2 of my cards and 1 of the dealer card. You see? Okay, that's if only 2 players, me and the dealer. Now, usually we have around 4, 5, even at one point, we have 7 people on the same table. So we have more cards to see, but less cards to expect because we have more cards on the table already visible. Okay, now, so I have to admit that I did estimation. I cannot do that precise. And to be honest with you, if we go back to this, right? If we go back to this, this is the exact probability, but in reality, this number has nearly no difference with this probability or probability of 0.06. They are too close to each other. Okay, they are too close to each other. Now, of course, the way I do the comparison is, for example, suppose if I have a king and a 6. This is for those people who knows how to play blackjack. This value is 16, which is a very, very bad situation. And the dealer supposed to have 2 cards, right? It will show one of them, and that one card is actually a queen, which has value 10. Okay, now then with my 16, okay, with my 16, what is the probability that the dealer wins against me directly? Now, that's if the dealer has 7, 8, 9, 10, jack, queen, king, ace. So he has too much probability, too many chances to win against me. In that situation, then I will ask one more card. Okay. So basically, he'll hit or fold there. Now, honestly, when I play blackjack, I don't fold. I don't surrender. Okay. In this situation, if I have 16 against face card, I hit. Okay, because 16 is basically a losing card already. By hitting, it's already a losing card. So by hitting, I can lose right away, but there's a chance I actually repair my situation by getting ace, 2, 3, 4, 5. Okay, so basically I hit not because I know I will win, but because I will take that last chance to improve my cards. Otherwise, this card is a losing card anyway. And the chance that the dealer actually just make it by flipping on the invisible card is actually a lot higher. The probability they win directly from with that is actually 8 out of 13. It's 8 out of 13. It's more than half. So in this original situation, given my condition right now, in this original situation, okay, the chance that I lose if I don't do anything is 8 out of 13. Okay, now when I hit the card, When I hit the card to carry, there's a big chance I lose right away, but that's still a chance, right? Okay, but there's a chance that I actually repair my situation. Okay, that's how I think when I play blackjack. Now, of course, I'm not teaching you how to play blackjack here. I teach you the basic on how to play blackjack. Okay. So it's quite interesting, huh? Until you apply that to gambling, you will never really know. Well, the other place you apply to gambling is on investment. Try to build your own company, or you buy stocks. Okay. When you buy stocks, for example, the stock price may increase, may decrease. If it increase, then you make money. Pretty much without doing anything but buying the stock. Okay, so it's easy come, huh? But there is a chance also the stock losing money. And basically you lose money by just buying the stock, not doing anything. But the thing is, like, when you buy a stock, you actually take a chance, take the risk of making money or losing money. And that's the consideration. Please don't forget that I have background in finance. Okay, so that's why the tax for stocks, especially for a long-term one, more than 1 year, the tax is only 15%, regardless your tax bracket. And the reason is because those people who buy stocks, they take significant amount of risk in making or losing money. Okay, so if you still don't really understand that, try to play stocks first. So try to buy some stocks and see what happens with you. Okay, yeah, that's what we call capital gains. Yeah, capital gain tax. Okay, capital gain tax, actually they are separated into two situations. The one short term, in which you hold the holding is less than 1 year, and long term, when it is more than 1 year. Okay, now if it is long term, then the tax will be taxed at 15%. Okay. Now the short one, I think that's the one depends on your tax bracket. Yeah. Okay, the short one. But I do not recommend you to I do not recommend you to become a day trader until you actually take classes to be a day trader. And my best, I think the best advice I can give you, if you want to be a day trader, don't use your own money, use somebody else's money. The fund managers actually doing that. Fund managers, they manage your money and put your money in stocks. They are the one actually trading using your own money. Of course, they have less burden because that's not their money, right? At the same time. Okay, so you make money for somebody else, but if you lose somebody else's money. That's not your money. Now the reason it's better to let a fund manager doing that, one of them mainly because they actually learn more about finance. Okay. Another reason is there is some psychological element of buying and selling stocks. If that's your own money, if that's all, or yeah, somebody actually sent me a message say that I have a pretty nice portfolio already and I still stay away from day trading. So yes, somebody say amen to me, huh? Yeah, it's quite risky. It's quite risky because when we buy the stock, we actually looking at the fundamentals of that company, and fundamentals of the company will give us the long-term outlook of how we expect the stock to perform, not day-to-day fluctuation. Okay, so yes, that's right. And the reason I believe that you have pretty nice portfolio, our friend said, of course I cannot say the name because he purposely sent that message to me in private. The reason you have a nice portfolio, it must be because you reduce your risk by not riding on the fluctuation, but looking at to the fundamental of the company. Okay, yeah, well, good for you. And actually, speaking about money, if you have a chance, this is outside of stats though, so it's up to you. You want to do it or not, and it has nothing to do with me. But I myself learned a lot by a guy called Dave Ramsey in money management, and he has a principle that everyone can be a millionaire. Yes, you don't believe it, but listening to him for quite some years, I know I'm going to be one. Yeah, and the principles he used actually very make sense without sacrifice. He is not all the way for money. He actually using money as a tool to obtain what we call the pursuit of happiness. Okay, like for example, one of them is delayed gratification, right? For example, instead of purchasing little stuff that we can buy right now with small money, we save our money to buy more value-lasting items. Okay, for example, the thing that I invest in right now is my house. I'm paying for my house, and house is one of very few property that when you buy, very likely it's not losing value. It's not like a car. You can buy a very good car. Once that car goes out to the parking lot of the dealer, you lost 10%. Nah, no, there's no point of buying that. Okay, so that's why I'm not really impressed with people driving good cars, especially if I know that person is still just a quote unquote a student, not working yet. In other words, the car that person buy is actually his or her parents' money. I don't have any appreciation to those people. Of course, I appreciate those who, even those a student, they buy their own car, even though that's like an ugly car. Nonetheless, that's your own car. You buy it with your own sweat. You earn it. That's what I call earn it. You work it out. And for you to be able to make it like that, it must be because of some dedication, waking up early, okay, hold your complaint, hold your grudge against your employer maybe, right? Okay, and then you kind of like have that, what do you call it? Customer may embarrass you here and there, but you just take it. You know what? I take it because what? I want to earn my money, for example, okay? But of course, there's at some point, you have to say something, okay? If you get discriminated in your workplace, of course, you need to speak up, okay? Well, anyway, but I do appreciate those people who earn their own money one or another way. Okay, let's see, come back here. Suppose I love talking about money, to be honest with you. Yeah, money has no meaning, in my opinion, unless you put $sign in front of that. You see what I mean? Then suddenly becomes something really good, right? Yeah, the only time you don't like money, numbers with $sign in front of that, when you have these 3 letters in front of that. Now, you don't like this one. But other than that, we love it, right? Okay? Yeah, and I hope you can earn more than me. Yeah, and no, that's not impossibility. No, I have seen people making more than me, and I'm glad for them. I'm happy for them. That's what I'm here for. Okay, I want you to learn your stats and use this in your work, make more money if possible, and help our friends, our family who needs help. Okay, and make this community a better place. Okay, now let's say we come back here. We will select this time. Let's say we select 3 elements without replacement. Okay, and the first one, find the probability that all 3, or maybe instead of 3 elements, I'm sorry, 3 students from this group. Remember yesterday we took only one, we select 1 student only, right? Okay, this time we select 3 different students. First one, find the probability that all three take math. Actually, I don't need to say it is without replacement though, because when I say select 3 students, it implies it has to be 3 students. Okay, you cannot select the same student 3 times. That's not what 3 students mean. Okay, yeah. What is the probability that all 3 take math? Part B, what is the probability that the first 2 English? Okay, and last one, not taking English. And part C, I think it's the most interesting one. Find the probability that we get at least 1 take English. This one is a bit more difficult. Now, let me ask you to work on this in 1, 2, 3, 4 minutes. Oh, the last one, let me give you a hint. The way we do this will be, we look at the complement. Probability of at least 1 take English is the complement of no English. Okay, which means you will compute 1 minus probability that 3 people you select, none of them taking English. Okay, it will take you 1, 2, 3, 4, 5 together with your break. We come back at 9:13. Okay, part A, what is the probability that all 3 take math? All 3 take math means the first one has to be math, the second one is math, the third one is math, right? Okay, so the first one to be math is 12 out of 30 probability times the second person, the second student has to be math also. So there are only 11 math out of 29. And the third person, there are only, because 2 earlier students already take math, right? So there are only 10 of them out of 28. Now, Thomas, how do you get that 12 out of 30 to start with? There are 12 students taking math. Okay, how about if, what if that person take English? Doesn't matter because that's not what it says, okay? It doesn't matter if these math students also take English or not. As long as that person take math, we are happy, okay? And yes, in your test later on, you need to show this first. In your test later on or your quiz, you need to show this first before you compute further, okay? Before you compute further. And when you compute, you can leave them in simplified fraction. It has to be simplified if fraction or in decimal. My computation shows I get 0.05419. What is the probability that the first 2 are in English, take English, and the last one not taking English? So how many people take English? 8 plus 5, that's 13, right? So 13 out of 30 times 12 out of 29 times, now the last person, so the first 2 are English, right? The first 2 are English. And then the last person is not taking English. How many people not taking English? There are 17 of them out of how many left? You already took 2 people out of
28.
Out of 28, that's right. Okay, and then anything after this is just computation calculator. Okay, 13 times 12 times 17 divided by the product of 30 times 29 times 28. I get 0.10887. Part C, what is the probability to get at least 1 take English. Now, if you think about it, let's see the situation. You are selecting 3 people, right? You are selecting 3 people. So there's a chance that you actually have nobody take English, only 1 take English, 2 take English, 3 take English. Somebody give me a pause. Did I type anything wrong? Okay, now, when we say at least 1 take English, it refers to either 1 or 2 or 3. Right? Either 1 or 2 or 3. Now, the thing is, to compute the probability of getting 1 English is actually quite difficult. Even just for 1, it's quite difficult. Even just for 1 English is difficult because you need to anticipate the situation where the first one is English, but the next 2 are not English. Or the first one not English, the second one English, and the third one is not English. Or the third possible scenario, you have the first one not English, the second one not English, yet the third one is English. Okay, so to compute even only 1 of these here, the first one is already hard, not to say that you need to compute all 3. Okay, now, so instead of handling such big computation, we turn our head, we actually compute the probability of the complement. Why? Because we know when we add the probability of all this event here, it has to be 1, right? Okay, it has to be 1. So if I know the probability of getting no English, then I also will be able to find the probability of getting more than at least 1 English. Okay, that's the idea. That's the idea. That's the idea. So, how do we change it? That's the idea. Okay, now then, let's compute what is the probability of getting no English. That will be 1 minus. The probability of getting no English means all of them has to be outside of English, right? Which is 17 out of 30, 16 out of 29, 15 over 28. Okay, that's what we will compute. So 17 times 16 times 15 divided by the product of 30 times 29 times 28. That's 1 minus 0.16749, which is 0.83251. Could it be that 2 or all are taking English since probability say at least 1? Yes, that's right. Yeah, when we say probability at least 1, it refers to 1 or more. So either 1 or 2 or 3. So this number here, the number that I get here, the number I get here actually refers to the probability of getting 1 or 2 or 3, not only 1. Okay, not only 1. Now, I believe you were referring to this situation here. Yeah, this situation, yes, only for 1. What I was trying to say is like, if I want to compute this probability of at least 1 as probability of 1 plus probability of getting 2 English plus probability of getting 3 English, if I compute it this way, probability of 1 English plus probability of 2 English plus probability of 3 English. Now, this one here is very hard to compute. I'm supposed to compute it this way. Okay, so instead of doing it a hard way, and I turn my head, I look for a what I call a back door. Okay, the back door is I look at the complement first. Because if I know the probability of getting no English, then the rest must be the probability of getting at least 1 English. Okay? I hope that explains it.
So, Professor,
Uh-huh.
when it says at least one,
Uh-huh.
or whenever I see that, do I just automatically go to 1 minus probability?
I will not say automatically. No, I will not. But most of the time, that will be an easier way for to compute. Now, is there a name for this 1 minus probability of no E formula? In our textbook in 5.3, they call that probability of at least 1. Probability of at least 1 is equal to 1 minus the probability of none. Repeat again. Sorry, I cannot hear you clearly earlier. As I know, there's no specific name for that, but a lot of textbooks call this probability of at least 1. Okay, well, anyway, I prefer to actually go a bit further into this. That's, we have this formula because of the following principle. Okay? When we say none or never, right, or never, is the complement, these two words here is the complement, or should I say the antonym of some. Like when we say someone in that room, it never refers to only one person in that room. It refers to existence of one person in that room, maybe more. Okay, so the word some is synonym to the word at least one. Okay, now then the word some, the phrase at least one is the antonym, is the complement of the word none or never. Okay, so imagine if my wife actually complained, I need to use capital letters, that's how I respect. Yeah, suppose my wife actually complained to me, Thomas, you never help me washing dishes. Then I will say I did once, and that's enough to refute her, right? I married her for almost 5 years already, but she can never say I never help her anymore in washing dishes because I did once. I know this is very cheap, huh? No, I told my wife, never use never. Just say that I hardly help you washing dishes, but never say I never help you washing dishes because I did once. I can even tell you the date because that's the only date I did that for the only time I help you. Okay, yeah, the word non, never is the complement of some or at least one. Okay, now let me say a bit more. The word all, the word everyone, the word all, the word everyone is the antonym of, so suppose to help you think about this, suppose I say all West LA College students are smart. Mostly smart, but I don't think all of them are smart. Okay, some of them actually not that smart. When I say smart here, not in the sense of school, but in sense of doing the right thing. Okay, now suppose somebody say all West LA College students are smart. How do you refute this sentence? How do you show that this sentence is wrong? How do you say to say that this statement is not correct? Now, a wrong way to do it, use red, wrong way, is when somebody say, well, you know, I'm Indonesian, so back in Indonesia, I learned English already, and coming to America, I need to learn a lot more, especially conversational English. And sometimes my Indonesian friends says, "Oh, you know what? For every sentence that you need to negate, just use the word not." But in this case, if you do so, it will be an overkill and to the point of offensive. Imagine if somebody say, all West LA college students are not smart. So you are saying that instead of all students are smart, which is actually a very good thing if it is true, to negate that by using the word are, not, inserting the word not, actually over negate it to the point of overkill. Now that's not the negation, okay? To say that all West LA college students are not smart. To negate the allness, the wholeness, all you need to do is actually to show some not. But not all not, okay? So the correct one is, correct way, you should say some West LA college students are not smart. Okay, now another illustration to depict this situation. Imagine your car. If you have a car, right? Okay, how many doors it has? My car has 4 doors, even though formally they say it's 5 doors with the one for the trunk. Okay, so it has 4 doors. Okay, now we say my car is locked if all 4 doors are locked. We say the car is locked if all 4 doors are locked. Okay, so what does it mean when we say my car is not locked? Does it mean all 4 doors are not locked? That's overkill, right? No, that's not what that's what it means. The negation of lock is unlock. Okay, so the negation of all 4 doors are locked is not all 4 doors are locked, not all. Okay, or to be more precise, to say the car is unlocked, you will say some door are not locked. At least one not locked, right? So you cannot say, well, my car is locked because 3 doors locked. Okay, majority locked. No, you don't call that car is locked if only 3 of the doors locked, right? I hope it makes sense right now. Okay, yeah, to say that a car is locked means all doors locked. Once any one of these door not locked, then you will say the car is unlocked. Okay, do not. There's no sense of majority in this case. Okay, you cannot say a majority of the doors locked, so my car should be considered locked. That's not right. Okay, that's not right. You know that's not right. Okay, you know that's not right. If you consider that right, show me your house. Show me a house. I get in there. You lock it except one door, right? Or except one window. I get in, and then will the police say that your house was secure? No, because you left one window open. Okay, of course, if I go there and steal something, I'm still at fault, right? Okay, but still on the police report, you cannot say that your house is secure. No, it's not secure. Okay? Don't worry, I will not go to your house and then pick up anything. I have my way to get something from other people. No, I'm kidding. Yeah. Okay, so going back to these formulas here turns out to be one very nice formula to have if we answer the question of at least one. Okay, yeah, and please remember this situation here. It's supposed to be something, it's supposed to be common sense though. Supposed to be common sense. But writing it down will formalize that better. My house is in heaven. You're welcome to steal anything. Well, if I can go to heaven, I don't need to steal anything. Just stay there. But thank you. Yeah. If I can go to heaven, even if that's your house, I will stay there. Yeah. I will stay there. Well, anyway, that's for that example. Okay. For this example. Now let's go into the situation where we will do have replacement. Now, suppose we will, let me open it a new topic. As if it is a new topic, but the idea is actually the same. Probability of selecting more than one element with possible repetition. In other words, the item or the element or the person we selected earlier may get selected again. Okay, now you will see the computation will be slightly different in an easier way. Suppose, for example, let me call that example one now. Suppose, for example, select one card 3 times with replacement. From a deck of, let me emphasize, that's a deck of 52 cards. From a deck of 52 cards. And then find the probability that all, let's say all kings Now you will see the following situation. The first time you take it, you select a card. The first time you select a card, the probability it's a king is 4 out of 52, right? Now the thing is you replace it, means you put it back. Now, then what happened is the second setup, the situation right before you do the second selection is the same to the first one, right? You still have 52 cards there, right? Okay, that's when you try to select the second card, right? Because you replace the first card you get, you put it back, right? Then the setup for the second selection is the same to the first one, such that the probability of getting another king, you still have 4 kings there because the king you selected earlier, you put it back. So you may select that again. Okay, and the number of cards you have in the deck is still 52. Okay, now likewise for the third setup, because the second card you select, it's a king, let's say, and then you put it back into the deck. Okay, such that the probability that you get the king, a king again in the third pick the third selection is still 14 over 52. Okay, and in decimal, let me ask you to compute the decimal. Let me ask you to compute the decimal. Use your calculator. Use your calculator. When you use your calculator, you may see the following. You may see this number, 4.55166. But you know probability cannot be more than 1, right? If you look further, if you go further, you see that toward the end, they show you E -4 on your calculator. Now, what does this mean? E to the -4, it actually, this is the way our calculator express what we call scientific notation. This actually means 4.55166 times 10 to the -4. That's what it means. Okay, so it is actually a scientific notation, and this to the -4 here, it means this 4 actually starts at, this 4 is actually, I think I should not use the word start, is at the 4th decimal place. Okay, because of that -4 there. In other words, if I actually write it in decimal instead of scientific notation, this will be 0.000. Now it's 3 decimal places. The 4th decimal place is starting with this number, 4.55166. That's what it means. Okay, that's what it means. You try. Suppose we select one card 3 times, or you can also say select 3 cards with replacement. Okay, suppose we select 3 cards with replacement. What is the probability that all 3 are, let's say, club? Let's look back. What is a club? How many clubs we have? This is what we say the club. Sometimes some people call that clover. There are 13 such cards in a deck. So probability that all 3 are clubs or clover means the first one has to be clover, right? The first one to be clover, there are 13 over 52. Actually, if you think about it, that's actually 1/4, right? The second one also 13 over 52. The third one also 13 over 52. Okay, so basically that's 1/4 to the power of 3. That's 1 over 64. In decimal, that's 0.015625 or 63 if you round to 3 decimal places. Yeah, in this case here, if you round to 5 decimal places, that will be 4.6. If you round to 5 decimal places here. Okay, that's if all 3 are clover. Now, how about this one? Find the probability at least 1 heart. At least 1 heart. So either 1 heart or 2 hearts or 3 hearts. Don't forget, when it comes to at least 1, okay, Not always, but most of the time, that's what you think first. Okay. Think about, is it easy for me to compute probability of getting no heart? Now, what is the probability that the first card is not a heart? Probability that the first card is not a heart. Now, you can see it this way though. Instead of seeing 39 out of 52, right? There are 39 cards, which is not hard. You can see it that way, but from proportion point of view, 39 over 52 is actually 3/4, because 13 over 52, so 13 out of 52 cards actually represent 1 out of 4 suits, right? Okay, so going back here, what is the probability that you do it 3 times? Yeah, you do it 3 times, and all of them not hard. Then it will be the probability the first one is not hard is 3 over 4. Of course, you can use 39 over 52. Okay, you can use 39 over 52 times the probability that the second one also not hard. Don't forget, it is with replacement. Okay, which means I put it back. Therefore, the setup for the second selection is the same to the setup with the first selection. Therefore, the probability of getting not a heart again is 3/4. And for the last one, still the same, is 3/4. Okay, that will be 1 minus 27 over 64, which is 37 over 64. That's the probability of getting at least one heart. Now, from here, I want to introduce to you something called terminology called independent definition. Events A and B are independent denoted by A perpendicular to B. Okay, so if you see this notation, I know a lot of instructors never use this. Actually, most instructor don't use this notation. But this is the notation we use in higher statistic and probability for independence. So A and B are independent. We denote it as A perpendicular B if the occurrence of A does not increase nor decrease the probability for event B to occur. So the word independent here is really in the sense of independent. It like doesn't matter what happened to A, okay? It doesn't make B change. Okay, so for example, to say that A is independent of B, it means that, for example, just for example, right? I have a big argument, let's say, with my brother, and I say I want to live independently from you. Okay, now to say that I independent from my brother, which means doesn't matter what he does. Okay, it doesn't change me into doing the same thing or not. Okay, so for example, when I say I'm independent of my brother, okay, and then I found out that my brother going to take a class at WLAC College, knowing that my brother there, does it increase or decrease? Does it change my decision in any way, increasing or decreasing my probability of taking the same class? Okay. Now, if I say I have a big fight with my brother, and therefore because he takes that class, I will not take that class, that's not independent. That's not independent because his decision makes me don't want to do that. Okay. So that's not independent, that's dependent. We just happen to do things oppositely. Okay. What do you call that if that's the case? If my brother's taking that class and because of that I will not take that class, what do you call that in our terminology? You remember? Hatred. No, it's not that. No, it's not that bad. It's not. No. In statistic, in statistic, of course, there's no such term hatred in our statistic. In statistic, we call that mutually exclusive. Okay, or in set theory, we call that disjoint. Okay, which means like whatever he does, I will not do. Whatever I do, he will not do. That's mutually exclusive. Okay, there's nothing we have in common. Now, independent is not. Independent means doesn't matter what he does, I will not change my decision. I don't even think about him. Okay, I don't even think about him. By the way, early stage of my relationship with my brother when we were teenagers, it's just like what I tell you. It's like we were to the point of mutually exclusive. If I, well, one thing, he's a smoker, okay, and I don't smoke. It's not that I don't like people smoking. It's just me. I don't smoke. Okay. By the way, my father-in-law smokes. My dad was smoking in when he was like 20 years old, around 20 years old. But actually, I want to share this with you so that you know more about me. Yes, but basically, me and my brother, pretty much to the point that whatever he does, I will not do. Whatever I do, he will not do. Okay, that's how bad we were. Right now, we are a lot better. We love each other right now. Maybe because distance, right? We need to miss each other to love each other. So if you have if you have some, that's why when we have some argument with somebody, one best way to actually get back together is give yourself some space to calm down and to see picture to see a bigger picture. Once you have some distance to your computer, for example, then you will see more than just your computer. Okay, instead of we focus on the source of argument, we see something else, that our blood and flesh relationship should actually put us together. Okay, yeah. That's one example. That's very personal story. It is true. Okay, and yeah, we love each other a lot more right now, a lot more. I can say that if anything happened to him, with the approval of my wife, I will come to help. Yeah. Well, I say with the approval of my wife because my wife is my number one. Okay. Yeah. Well, anyway, to give you some background about me, my dad had cancer. He's still alive though, but he had, we can say, the 5th stage cancer. In 1982. That cancer is called nasopharyngeal carcinoma. That's the cancer that if you catch cold, okay, I'm not saying if you catch cold, that's a cancer. No, that's not what I'm saying at all. Okay, but if you can imagine where your mucus located, right behind your nose, above your throat, sometimes to the point that you cannot hear anything. Okay, that's the location of the tumor. Okay, that's nasopharynx. Okay, now my dad had that fifth stage cancer in 1982. And at that time, doctors said that he had only 2 months left. And that's a group of doctors. One of them actually a Muslim and say that even if, I'm Christian, by the way, okay, I'm a Christian, but the doctor's a Muslim, and that doctor say, even if our God is great, okay, even with our God is great, you have only 6 months. It turns out that it's greater than that. He's still alive. He's still alive. What is Christian Dior? Okay, yeah, he's still alive. Now, when I say I'm a Christian, by the way, and a lot of people think that Christian don't like Muslims, please don't think that way, at least about me, okay? Because when I did my undergrad in Indonesia, and most of my best friends are actually Muslim, okay? Of course, I want to create a safe environment for all of us, okay, to engage in meaningful discussion. And when it comes to religion, for example, I want you to feel safe, even if your religion is not the same to mine. And I'm not devoted anymore. I'm not devoted anymore. At that time, I was still devoted. But I want you to realize that my Indonesian background makes me very, very close to a lot of Muslims, and I have very, very good impression about them. Okay, I have very, very good impression of them. Every time I go back to Indonesia, I still contact my friends and we still go eat together, have fun together. Okay, well, anyway, my dad had fifth stage this cancer in 1982, and my brother had the same cancer. The third stage, when it was discovered of the same cancer in 2004. I'm sorry, 2003, not 2003. It's 2003. Now, I remember that's 2003 because at that time, I was supposed to graduate from Castle LA with my master's. But because I found my brother had that cancer, then I was supposed to transfer to UC Irvine for my PhD. But because of that, I postponed for 1 year. And because I postponed for 1 year in 2004, I ended up going to USC instead with a much better scholarship. Okay, now, I'm proud of my USC background, but I'm not super proud, like super big deal about that. The main reason I went to USC, because I was diagnosed with the same cancer at that time. And the good thing is, because my brother was diagnosed with that cancer in 2003, and he went to Taiwan for his treatment. And we didn't have family, like very close family there. So there was one time he needs to start his radiation for his cancer, and we didn't have money. I have the money, but I need to, if I send it there, it takes like a couple of days. So instead of sending it there, I actually took a flight there so that I can bring the money there. And at the same time, I did my checkup there too. Okay, because this type of cancer is not that common in America. So when I went to an ENT, it took them a long time to actually, even just to set up an appointment for the lab. So I decided, you know what, I need to bring the money there. Let me do the checking there too. And when they checked me, they found out that it's already in my blood, even though there's no tumor yet. You know, and at that time, I actually prayed very hard. Well, because my dad, my brother at that time had a kid on the way, and I was still single, and I kind of pray, you know what, let us release us from this and deliver us from this, and then if possible, let me get the cancer and set him free. And we thank God that my dad still survived, my brother survived. When you see my brother, you don't believe that he had cancer that 17 years ago. In fact, my dad right now is in the old stage. He is old. He is 70 years old with very heavy radiation and chemotherapy in 1982 for 5 to 8 years period. It took a lot of toll on his body. I wonder if I have his picture on my Facebook. I shared it with you last time. In future. But if you see him like around 10 years ago, if you say this is almost this is 38 years ago, right? Yeah, my dad's situation, that's 38 years ago. If you see him like around 20 years ago, you won't believe that he ever had this fifth stage cancer. With the radiation that he had, he lost all his hairs on his head. Now, when I say hairs, not only his hair, like the long hair that you have, it includes all the hair on his head, including his eyebrows. And he basically lost all his teeth also because of the very, very aggressive radiation. You know, right now, of course, in 2003, the technology is a lot better. Okay, so it takes, and my dad was discovered with that cancer, even though not that early, but earlier because my dad already experienced what he had at that time. So my dad kind of like, oh, you may have the cancer I had before. Let's go see the same doctor. So the doctor who took care of my dad, also the doctor who took care of my brother in Taiwan. Okay, and according to what he said, that whoever had that cancer, whatever stage that person was in 1982, already passed away. The reason I get with my current wife, actually this is my second marriage, with my current wife is because her friend, my wife was actually my high school friend, and her friend had the same cancer. Unfortunately, when she contacted me, her friend contacted me, she already did a surgery. And when you have this type of cancer, nasopharyngeal carcinoma, you're not supposed to have surgery. Yeah, too many nerves actually going through that area, such that any surgery will only spread the cancer right away. Nobody had surgery survive more than 1 year after that. Yeah, for this type of cancer, okay, for this type of cancer. Now, because I have direct family actually get this type of cancer, I myself learned about this cancer a lot. The formal name of this cancer is nasopharyngeal carcinoma. Now, I know some of you may experience some type of this kind of situation in your family, like cancer situation. The purpose of me sharing this story, not to discourage you, not to kind of like bring back the trauma. Trust me, when my dad, as the only breadwinner in my family at that time, had this cancer, it's a very take a very big toll on him, and also us as a family, at least financially, and of course also mentally. But hey, we went through that, we survived. So I hope my story is an encouragement in itself, that an encouragement for you, that hey, you know what, at least I know somebody who went through that and survived. Not to say that, imagine an Indonesian like me, right, from a very poor family, can come to the United States instead of taking classes here. Of course, I took class here, okay, but I came with a green card, and then I took class, and now I teach in America instead of just taking classes, right? And now my family already live in a much better house, and I myself paying for my house right now. Okay, so of course we need to be patient though. It's a 40 years journey, okay, but I can say that my family cannot be happier right now. Okay, yeah, so if you have some difficult time right now, especially with this COVID, please be strong, try to get your try to get people around you to support you, if at least mentally. Okay, we need to stay sane, stay sane instead of being insane with the situation, get overwhelmed with the situation. Okay, yeah. I hope this is not a story of discouragement. Instead, it is an encouragement that if this is the worst time in your life, then things can only get better. Okay, that's the dean, Dr. Walter, said a lot of time in his email to us. Okay, now come back here. Events A and B are independent if the occurrence doesn't increase or decrease the probability of another event to occur, which is actually the case we have earlier when we have replacement. When we have replacement. Why? Because whatever happened in the first pick of the card, it doesn't change the situation for the second pick. In other words, if the first card is king, the probability that the second card is king is 4 out of 52. Now, what if the first card is not king? What if the first card is not king? Because you put it back, because you put that card back, the probability that the second card in itself is still 4 out of 52. Okay, now another illustration for this independence, for example, is like when we toss a coin. That's actually the standard textbook example. Toss a coin twice. Now, if you have coin next to you, you can try to use it, just to help you figure out my illustration. Now, the probability that the first one is tail, suppose that's a fair coin. The first one is tail is 50%, right? Okay. Now, what is the probability that the second toss is also a tail? Still 50%, right? It's still 50%. Now, what if the first toss is not a tail? Does it change the probability the second one to be a tail or not? You will see no, right? It won't change. In other words, when we toss the coin the second time, we don't need to look at what we get in the first place. We don't need to find out what was the outcome in the first toss, right? So you will see that the first toss and the second toss are actually independent. Okay, now one last example. You can call this illustration, you can call this example. I know one person happens to be a girl, a friend of mine, which is a girl, not a girlfriend. Well, you can call it girlfriend, but not in the special relationship term, but as a girl, which is my friend. She has hard time to wake up. She has hard time to wake up. So she actually do it this way. Okay, she told us that she put an alarm actually next to her on the table next to her, and then she put another alarm actually on her way to the shower room, and put one alarm in the shower room. Now, of course, these three alarms should be independent, not coming from the same source of outlet, right? Okay, and it's independent. Why? Because she has a habit, if the alarm went off, she will just shut it off. Now, but then she put another one here, so that for her to shut it off, she needs to walk a little bit. And to shut this one off, she needs to be in the restroom, in the restroom already. Okay, now then suppose, think about this. Suppose this is Thomas. The probability that Thomas being awakened by this one alarm is 0.99. maybe 0.95. So 95% chance Thomas will be awakened by this alarm. Another one is 95%. Another one is another 95%. And of course, to wake you up, you just need one alarm to wake you up. You don't need all three, right? You don't need all three. So the probability Thomas wake up is the probability that at least one alarm went off. Okay, so the probability that each one of these alarm actually went off, not suddenly not working, is 95%. Now, why Thomas want to use 3 alarms instead, and we need them to be independent, because by having 3 alarms, the reliability of the combination of these 3 alarms will be a lot higher. Let's see, what will be the probability I wake up? That's if at least one of them went off. That's 1 minus the probability that none went off. Now, what is the probability that all 3 not working? What's the probability that this one is not working? Zero 0.05, 5%, right? Okay, so the probability of not working is 0.05. Now, you need all 3 of them not working. So that will be the probability of 0.05 for the first one not working times 0.05 for the second one not working plus times 0.05 for the third one not working. That will be 1 minus 0.000125. So the probability that at least one of them work, therefore Thomas will wake up, is 0.999875. A much improved probability compared to if I use only one alarm. Okay, I have 5% chance of not waking up at the right time, right? So suppose on Monday, you need to wake up early for your test, right? Okay, now I do suggest you not using your phone only to wake you up, especially if you don't charge it, okay? With me, I have natural alarm. Beside my phone, I have my wife, and I have my son, and I have my daughter, okay? Once one of them went off, I mean, if my daughter, my 5 months, 6 months daughter cry, it's quite loud, and I will wake up. Actually, she's the best alarm, you know. Okay, now notice that using more than one, they have to be independent, though. Okay, they need to be independent to improve this reliability a lot higher. From the only one alarm, you get 3 alarms. And this is not expensive alarm. I actually buy 3, you can think of this as 3 cheap alarms, but because I use 3 of them, it's a highly improved alarm instead of using one expensive alarm. Okay, yeah, I think I need to stop here. It's 5 minutes over time. It's 10:10. Again, don't forget that I will post a quiz. I'll post a quiz which is due on Monday, 8:06, just like your quiz one. But this time I will not give extra time anymore. No more, no more, no more, no more. I have 3 students say, Thomas, something happened to me. Thomas, I cannot upload it. Thomas, I misunderstood the deadline. I thought it's 8:06 p.m. You know, I purposely use ugly number here to attract your attention, actually. Okay, if I use 8 o'clock, that's way too common. 8:06, then you start thinking 8:06. Dude, why that strange? Well, anyway, it's strange anyway. Okay, so yes, I will post it, and I will suggest you to start working on your on this once I post it. And you can start looking at my old tests already. Most of the problems, if not all, already doable. Okay, see you then tomorrow.